So this is video 3, and to recap, how do we generate a current in a wire? Well, you need to have a varying magnetic field whose lines of flux cut a current carrying wire. And if you remember, there were 3 ways that this could happen. 1, the magnet moves. 2, the wire moves. Or thirdly, the magnetic field varies in some way. It changes. Now what we have up here is a really simple version of a generator. A hand-spun dynamo where you are physically moving a wire inside a magnetic field which is fixed. And this is what generates current in the light bulb. And just as a simple sideline, how do we increase the current? Well, if the current depends on cutting the lines of flux, then we can increase the current by making the flux lines be cut faster. Because remember, it was to do with the rate of line cutting. How quickly do you cut the lines? So you can generate a higher current by moving either the conductor or the magnet, or changing the magnetic field faster. You can use a magnet with a stronger field strength. You can use a coil. Okay, so this is to do with flux linkage. You can have more than one wire. Or you can increase the area. This is because linkage, mathematically, we can look at our relationships just to clarify this. If the current or the EMF that you are generating depends on how quickly you are cutting the lines or the rate of change of flux, right? So if we look at our relationship, if you make the field stronger, if you increase the area, if you increase the flux linkage, the number of coils, then we can see that these are evident in our relationship that we were using in the last video. Here's some simple questions to keep you warmed up. Stop the video and give them a go. So hopefully you didn't find them very difficult. Number 1, it won't work with plastic because it's not a conductor. The electrons inside the plastic won't move. Number 2, how would you move the copper wire to induce the highest EMF? Well, it has to be perpendicular to the direction of the field lines. Okay, so it would be into and out of the paper. For B, 0 EMF. If you move the wire parallel to the field lines, then you would get 0 EMF. Or if you were to move it up and down. Okay, so remember, the movement must be perpendicular to the field lines and the direction of the current flow. Well, number C is almost a little bit silly. It's just a loose wire, so it can't be in a current. It can't be any current because it's not in a circuit. Okay, so this is really an important situation that comes up a lot in exam questions. Suggest explanations for the shape of the graph shown in figure 11.8. Right, there are 2 aspects to this. The first one is the shape, and the second one is the direction, the plus and minus aspects to it, which we're going to come back to a little bit later. So I'm just going to talk about the shape for now. What happens when you drop a bar magnet inside a coil here? Now, the EMF, which is what we're measuring, depends on how quickly you cut the lines of flux. So we have a proportionality, and that EMF is going to show that an increase, okay, as the magnet gets closer. So as this magnet gets closer, because the lines of flux, if you remember a bar magnet, okay, I'm going to do a bad drawing of one here. A bar magnet, okay, has more closely packed lines. Let me draw that properly. Okay, I realise that is not a hell of a lot better, but it will do. So as we get further away, right, so out here the lines are further apart. So as this is quite far up, the lines are far apart, so the lines are not cut quickly. But as the magnet falls through and gets closer, there is an increase in the amount of lines that are cut per second, right? So you get a peak. When it's in the center, then you have like a maximum. Okay, that's when its field lines are more densely packed. So therefore you get a peak. And then as the magnet falls through and starts to move away from the coil, then the number of lines in a space is less and you cut less. And so therefore it goes back to 0. Okay. Now the question doesn't go into any detail about whether this is accelerating, going at constant speed, if it's just being dropped, but you also need to take into consideration the fact that it is getting faster. So you might register on some of these questions that this bit is a little bit smaller than this in terms of time, but there's no question of that here. But it is getting faster as it drops. So we have the idea of these field lines being closer together, closer to the magnet, but also the fact that it's moving quicker, so the time aspect is reduced. Now the direction, why does it flip? We're going to look into now, and I'll come back to this example later. Here we have pretty much what I just said written out, so if you want to stop and read the text for a moment, just to clarify. So the direction of this magnetic field, right, let's have a look. The law of conservation of energy, this is something you should be familiar with, I hope. And it's a phenomena which affects this produced EMF. In the example before, when a magnet falls, it induces a current in a coil which creates its own magnetic field. Right, so that's the next step. Okay, we haven't talked about this. But when you induce current in a wire, what does a current carrying wire then produce? It produces another magnetic field. This is just insane. So what we're getting here is a magnet that is moving through a coil, an EMF inside a conductor, which is inducing a current, and then that current is generating a magnetic field. Now, how do we know the direction of that magnetic field? Well, that was your left hand rule. Do you remember, with your thumb pointing this way in your right hand and your fingers then showing you the direction of the circular magnetic field lines. Okay, so for example, here we would have the field lines moving this way. Okay, using your right hand rule, just one thumb pointing one way and your fingers curled over. So, right, let's go back to the text. You have a magnetic field that is created. Now, what is the direction of this generated current and this generated field? Well, it has to do with conservation of energy. If the magnetic field created here, right, was so that it attracted the South Pole. So imagine that the coil here was generating a magnet which was attracting this magnet. So imagine that this was north, right? And it was pulling this magnet further in. Then it would accelerate quicker. You would end up creating energy. What? Hang on, let's have a think about that. Where is the energy coming from? Well, this whole setup is happening because we're getting gravitational potential energy becoming kinetic energy and then electrical energy, I guess. Now, what you can't have is a situation where this electrical energy gives more energy to the falling magnet than it had in the first place. So you can't have this accelerating situation, It's impossible. It violates the law of conservation of energy. So what actually does happen is that the current that is induced in the wire is such so that it makes a south pole. So have a think about why. What would be the consequence of that? If it generates a south pole, then it repels the magnet that's falling through the coil. It's like it's trying to stop the very change that is making it happen. And in fact, that is what happens. This is the basis for something called Lenz's law. Now, there isn't space in your booklet to write this down, so you're going to have to make your own notes. It is very, very important. This is a very common question in the IB exam. Lenz's law, it states that, and boy do you need to learn this off by heart, the direction of an induced EMF is always such as to oppose the change in flux that produces it. Okay? So if we go back to this example, the current in the wire is such that it produces a pole in the magnet around the coil that will repel the falling magnet. So an induced EMF produces a south field upwards and opposes the motion of the magnet. Okay, and this ensures that the law of conservation of energy is adhered to. So let's go back to that graph then, and let's do a full analysis of what's going on. So initially you have this coil. Let me tidy this up. And as the magnet approaches, okay, a south magnet is generated in the coil. Now, if we have a look at this convention, we did this right at the beginning in the standard level topic, but you can either use the corkscrew rule, the right-hand corkscrew rule, or you can do this sign convention. You can see the current is flowing this way, okay, to make a south pole. Now, why is this a south? Because this needs to repel. Okay, it's trying to push that magnet away. But the gravitational force acting on the magnet is greater. It's never going to be strong enough to stop it. It's always just going to try and slow it down. Now, when the magnet just crosses that half point, okay, it's now falling this way. And what it's doing is it's now moving away from the magnet. And this time, in order to stop this from happening, to stop the magnet moving away, what the coil needs to do is now try to attract the magnet, okay? Now, how is this coil going to attract this magnet? Well, this is north, so it needs now to have a south pole here, okay, under the coil, which would make a north pole up here. Okay, so in order to make a south pole here, the current now needs to flow in this direction. Okay, so basically we flipped poles. Now what does that look like on the graph? Okay, so we have this increasing EMF in the positive sense. So basically the current is flowing in this direction to create that south pole here, and then as it reaches the midpoint, it would flip over. So the current now starts to flow in the opposite direction, this time to attract the magnet. Here it's to repel it. Okay, until it gets to this peak point where the lines are being cut, the maximum number of lines are being cut, and then it would go down again into the center, or to the zero, okay, as it moves further and further away. So the change in direction of the current is a direct illustration of Lenz's law, which is here. So now we understand this minus direction, the fact that the magnetic field, the new magnetic field, is minus to the inducing magnetic field. We can now look at the full Faraday's law definition, which is that the EMF is equal to the rate of change of flux including a minus sign to denote Lenz's law. So, well, hey, we've done it. We've reached the end of our two very, very important points within this topic, Faraday's law and Lenz's law. Okay, so this brings us to trying to figure out the direction of currents and Fleming's right-hand rule. So it's exactly the same as left-hand rule, but this time we're going to use our right hand. And it's only to deduce the new EMF. Okay, so in a situation where you're inducing current, not movement, this is not the motor effect, this is just for movement, then you would use the right-hand rule. So let's try a question. A conducting rectangular loop enters the magnetic field shown. What is the direction of the conventional current, clockwise or anti-clockwise, induced in the loop as it enters the field? So use the right-hand rule for this. Okay, so hopefully you remember how to use the right-hand rule, I'm hoping. So your first finger is into the page, right? Because the arrows of the magnetic field, remember, first finger is the magnetic field. The thumb, so you show the movement this time with your thumb, and your second finger should end up pointing downwards. So if the current is moving downwards in this wire, then it denotes an anti-clockwise flow. And that's pretty much it for this topic. Okay, so we're going to move on to current generation, which is actually a little bit easier.